Today we're going to take a look at polynomial equations. Specifically, we're going to look at what we mean by that. What is that language referring to? And then also how to solve some very introductory level ones. So that's what I screwed up on the notes that or on the homework that I'm not going to hand out to you and email it to you, is that it went farther than I anticipated us going today. So to start with, we're going to take a look at what's called the zero principle of multiplication. So the zero principle of multiplication says that if you have two numbers, A and B, and they multiply together to give you 0, then either A was 0, or B was 0, or they both were. And you guys know this to be true from arithmetic from early on. Right? When you were doing the multiplication tables in 2nd grade or 3rd grade or maybe even 4th grade as review, you went through and you filled in all the ones that the answer was 0 for, like probably automatically, because they were really fast, right? If there was a 0, the answer is 0, 0, 0, 0. But nothing else would ever have an answer of 0 if it wasn't something multiplied by 0 to start with, right? Okay, so this is a fact that you're very familiar with when it comes to just number operations. And because this is true, we can actually apply this to variable operations as well. And here's how. So what we have right here is we have something that we could call A. I'm going to write it above, actually, so don't run out of space. And this piece that I can call B. There are two factors that are being multiplied, and the product of them is 0. So what that tells me is that either the A, which is the first set of parentheses, or the B, which is the second set of parentheses, must be equal to 0. So therefore, we can set up two different equations that say that thing in the parentheses that I called A, it could be 0, or the thing in the parentheses that I called B, it could be 0. And this is why this works. Now notice, that's very special to the number 0. If the number 3 had been on that side, this would not be a true statement. Okay? I can get 3 by multiplying things together that don't have a 3 in them. I can. Okay? So this is because it's 0 that this works. And then what we actually have to solve are two simple linear equations that we've solved, or at least we've solved this type of before. So on the first one, 5v plus 3 equals 0, what would I do first? Subtract 3 from both sides, you got it. That would leave me with 5v equals negative 3. And then what? Divide by 5. Okay, so I'm kind of out of space, but here this now is v equals negative 3/5. Let me move this over. All right, second one, what could I do? Subtract what, Josh?
9.
You want to do the 9? Okay. So I've left with negative v on the left, and now I have negative 9 on the right. So my second answer is that v equals 9. So I get potentially two different answers because I had two different factors, right, sets of parentheses, each individually that could have equaled 0. Okay, so what this 0 property does is it breaks down something that's not linear into pieces that are linear so that we can solve them the same way we already know how. So we're going to try another one. This one looks messier.
Wait, so that's all you do?
That's all you do. Yes, ma'am. Two answers, all you do. Number 2 looks like it's harder because there's like a third thing in front that's negative 4. So what you could say, we'll say it once and then we'll never say it again, is you could say that we're going to set each of these 3 factors equal to 0. But what really happens here? Whoops. You could distribute, but you don't need to. Look back at what I've highlighted. What do you see here that's says negative 4 equals 0. What's that? There's no variable. Can somebody just say that's not true? Yeah. It's not true, right? Negative 4 does not equal 0. This gives me no answers, and it's partly because of what you just said. There's not a variable there to make that possible, right? So I can write down negative 4 equals 0. I mean, I can write it, but it doesn't yield any solutions. It's a no solution part of this particular setup. And if you distribute it like Josh said, it would end up falling out in a little bit later too as a division step. So it doesn't yield anything from that perspective either. All right, so the other two pieces are fairly friendly. How will I solve y plus 3 equals 0? Yep, I would subtract my 3. So what was y going to be equal to there? Negative 3. How about the next one? Plus 5. So I have negative y equals 5. And then what? Divide or multiply by negative 1. We'll divide this time, sure. So what would y equal from this part of the equation? Negative 5. Again, two solutions, because I really have two sets of parentheses with variables involved to allow that to happen on this one. Now, both of these types of equations are something called polynomials. That's why we've titled this polynomials, and we'll get a little bit more into that later. But I want to take one more. In fact, no, you know what? We'll do it now. Let's do it. There we go. Polynomials. So these are both types of both examples of polynomials. I'm going to give you a few other examples of polynomial expressions. So some examples of polynomial expressions would include something like 1/2 x squared plus 2, or 3x cubed minus 7x plus 4, or just 4x, or 6x squared plus 2x minus 1. These are all examples of polynomial expressions. If you put equals something, then they'll become polynomial equations. Okay? Let me give you some examples of things that aren't polynomials. X to the negative 3 plus 2x minus 7. Square root of x squared plus 2. 1 over x plus 3. These are not polynomials. So see if you can tell me what you notice to be different between the set on the left and the set on the right. What's different? On the right-hand set, right?
Yes.
Okay, so on the right-hand side, I see a negative exponent. I don't see any negative exponents on the left one, correct? So that's important. Polynomials don't have negative exponents. What else? There's a radical over like variables, right? Radicals over numbers are not problems, but radical over variables. And we see that happening in the second set. So polynomials don't have radicals with variables underneath them. What else do you see? Yeah, again, it's the variables, right? So like I have a 1/2 on the left-hand column, but on the right-hand column, it's the variables that are in the denominator that are the problem. So no negative exponents, no radicals or denominators that have variables in them. So in particular, the expressions that count as polynomials are of the form, and this is super weird looking, but just jot it down. A sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... plus a2 a2x squared plus a1x plus a0. Let me just tell you what all that means. All of these things that are the a's, a0, a1, all the way up to an, these are just numbers. Okay, so like in my examples, they're the 2, they're the 1/2, they're the 7, they're the 6, they're the 4, they're the 3, the 4, the 2. They're just numbers, okay? All of those a sub somethings are numbers. And then all the components that have this part are simply powers of x that are positive powers. And we also get sort of for free the constant at the end. That's totally fine too. Okay? So a specific type of polynomial, and it's the examples that we've been working with so far, are actually called quadratics. So a quadratic is a polynomial of the form ax squared plus bx plus c, again, where the a, b, and c are numbers. Okay, they're just constants. So it's a polynomial because it fit the description I had before, but it's a special case, in particular the case where I have an x squared term and nothing bigger. Quadratics have x squared and nothing bigger. There's no x cubes. There's no x to the fourths. It's x squared and nothing bigger. And this value, in this case, I'll use the a as my example. This value a at the beginning is a special name. It's called the leading coefficient. So the leading coefficient is simply the number in front of the term that has the highest degree. Okay, so a is called the leading coefficient because it leads the highest exponent term. Okay, I want to introduce you to 3 more terms, and then we'll get back to doing some examples, because I really don't know if I can say the examples without using these terms, and then I feel like I'm sort of being unfair to you to use them without saying what they are. So the 3 terms that we're going to look at here are monomial, binomial, and trinomial. So a monomial is a single termed expression. For example, if I just had 4x, that's a monomial. Okay, so remember, terms are separated by addition and subtraction. So 4x combined with multiplication is actually 1 term. A binomial is 2 terms, so it would be something like x squared plus 3. 2 terms, because it's 2 pieces that are separated with the addition. And then a trinomial, which is what we've actually been, are about to work with. It's a couple examples still away, but we're about to work with them. Are values that would look, well, they would look like the quadratic that I just wrote down. So I could have something like x squared plus 2x minus 7. It's 3 terms separated with addition and subtraction. Trinomials. Okay? I don't ask definition questions. I'm never going to ask you, say, define monomial. I'm not going to do that. Okay? Define a polynomial. I'm not going to do that. But if there's a direction set that refers to monomial, you should know what it means. If there's a direction set that says the word leading coefficient, we're going to have that in our directions in a little bit, you should know what that means. It should be something that you can handle in a directional sense. So let's take a look at a couple of examples. I skipped them because I felt like they fell better. Actually, in this different order, but that's okay. We're going to talk about common factors. So we've looked at common factors before. We've found like least common denominators, right? This is a similar idea. So when we're factoring, a good first step to do anytime you're factoring is to find the greatest common factor. So you take all the terms you're looking at. If there's 2, that's how we're going to start. There's 2. You just look at 2 things. But maybe you'll have 3 terms that you're looking at all of them, and they all happen to be even, so you know that their greatest factor maybe is a 2. All right, so you're looking at a set of terms, and you're looking for their greatest common factor for all of them. And then when you factor that out, what you're left working with is usually something quite smaller than where you started and easier to work with. That's the idea. It's kind of like when we reduce fractions, right? We try to factor out anything that they have that you can reduce them by. Do they both divide by 2? Then we divide them by 2. Do they both divide by 10? When we divide them by 10. It makes the fractions image smaller and easier to work with. Okay? That's the whole idea here too. So, are we ready for an example of this one? A couple people still writing. I'll hold off. Okay, am I good? Okay. All right, so the first one, number 3, says 6u squared minus 12u equals 0. So just vocabulary-wise for a moment. Is this a monomial, a binomial, or a trinomial? It is a binomial. There are 2 terms separated in this case with subtraction. It's a binomial. What is the leading coefficient of this binomial? It's a 6. And it's not because the 6 is the first thing in the list. It's because the 6 is the value associated with the u squared, our highest degree term. Okay, good job. All right, so what we're going to do is we're going to consider both of these terms, and we're going to ask ourselves, what do they have in common, both the number parts and the variable parts? So let's start with the number parts, 6 and 12. What do they have in common? They have a 2. Anything bigger? A 6. They would have a 3 in common as well. So 6 is the biggest though, right? They both divide evenly by 6. So I'm going to put a 6 out here. I'm going to leave a little space, and I'm going to put a set of parentheses. Now let's look at the variable parts. One of them is u squared and the other one is u. What do they have in common? U. So out here with the 6, I'm going to put a u. Now, what goes inside the parentheses is basically the division. If I took 6u squared and I divided it by 6u, what would remain? What was it? Just a u, right? 6 divided by 6 would be 1. U squared divided by u would be u. So I'm left with a u. The sign stays the same, so this is subtraction. And then we're going to do the same thing again. 12u divided by 6u.
It would be just -2.
Good. It would just be the 2, and then the sign between them, like we said before, would be negative because the signs stay the same. Now, the cool thing is at this point, where we really have found ourselves is essentially where these problems started. 2 pieces multiplied together equals 0, right? 6u times u minus 2 equals 0. So we're going to set each piece equal to 0. Because the only way this equals 0 is if one of them equals 0 individually. 6u equals 0, what do I need to do? Divide by 6, what is u? 0, good. U minus 2 equals 0. Plus 2, so u is equal to 2. If I wanted to make sure that these really are solutions, and I didn't make a mistake along the way or do something inappropriate, how could I check to make sure these really are solutions? Plug them in. Trey, where would I plug them in?
Plug in 0 by the first 6u squared.
Right. We'd plug them in at the very beginning, right? Not the part I factored, but the very beginning to check and make sure that they really work. Good job. Let's try another one then. Y squared equals 19y. What is different about this problem than the last one? It's not equal to 0, right? And the whole 0 principle doesn't work if it doesn't equal 0. Okay? Gotta equal 0 to start. So how am I going to change that?
We can just subtract the 19y.
Yes, sir.
And
Yep. Okay, so on the left-hand side, I now have the y squared minus 19y. And on the right-hand side, like Josh said, I have equal to 0. And once I've done that, it actually looks a lot like the last problem, doesn't it? Where it began. So now again, I can look at these pieces and I can say, what do they have in common? What does y squared and negative 19y have in common with each other? A y. And that's it, right? Because they don't have any, the y squared doesn't have a coefficient that's not 1. So I don't have any comparison to make there. What is y squared divided by y? Just y, right? Because y times y is y squared. What about negative 19y divided by y? Okay. Yeah, just the negative 19. Does that look good? Everybody good with that point? Okay, what would I do next? Okay, so one of the pieces is already done. Y is equal to 0. The other one is y minus 19 is equal to 0, and we would add a 19. So what would y equal in the second piece? Yeah, 19. Okay, so those are both binomial examples. The last examples that we're going to do are all going to be trinomial examples. So there are two different ways I'm going to teach you, and these are not even the only two ways to do this, okay? I'm not going to lie. I'm just going to only teach two methods. If you have another method and you want to come ask me if it's okay to use, come ask me. The first method I'm going to show you is called the AC method. The AC method lends itself very nicely to more difficult factoring later on, which is why I want to bring it up. It feels a little funny to do it right now, but we're going to do it anyway. So the AC method says that we do the following. I've got this example here, u squared minus 7u plus 10. And some of you are probably doing this very quickly, or at least maybe from some other method. You've got another idea in your mind. So just hold off on the other idea for a minute. I'm going to show you two of them, and we'll start from here, okay? So what we're going to do is we're going to multiply. Do you remember I said, I'll write it up here, that a polynomial that's a quadratic has the equation ax squared plus bx plus c, right? So here's an a, and here's a c, and here's a b. Okay, that's the AC that this is referring to, is that a and that c, okay? The leading coefficient and the constant at the end. So the AC method says I'm going to multiply a times c. And these are all just numbers. What is the a value for the first, problem number 5? It's 1. There's an understood 1 here. Is everybody good with that? Okay, so this is 1 times the c value. What is the c value in this problem? It's 10. So a times c is going to equal 10. We'll come back to that. The b value is simply the coefficient that's attached to the middle. What's the b value for this? It's 7, and it's actually negative 7. Okay, so we're going to keep the sign with it. So here's what we do. I'm going to write down a little bit, even though I know you don't write on the problems themselves later, is that we want two numbers that multiply to the AC value, whatever you get there, and add to B. So in this problem, I want two numbers that multiply to 10. So to give me some options. What are two numbers that multiply to 10? 2 and 5. What else are there?
1 and 7.
They have to multiply to 10.
Oh, sorry, 1 and 10.
1 and 10 would work. And this one doesn't have any other choices, right? Which of these, if I put addition here instead, right, 2 plus 5, 1 plus 10, which of these add to negative 7?
That would be 2 plus 5.
Well, 2 plus 5 adds to 7,
Yes.
right? So I actually could have also done negative 2 times negative 5 here, right?
Yes.
And that's the one. Negative 2 and negative 5 add to negative 7 and multiply to negative 10. Let me show you how I'm going to use them. And this is going to feel funny. Just bear with me because we're going to use it in a later lesson in dealing with this, okay? So we're going to take our variable that's at the beginning, x squared, and we're going to leave it there. And we are going to rewrite the middle term, the negative 7u. And it's going to be rewritten as negative 2u and negative 5u. And it doesn't matter the order. If you'd put 5u first instead of 2u, you're fine. No problem.
Does it matter that you put an X?
Oh, well, we'll fix it, yes. They should match. Thank you. Okay, so all I did with the negative 7u is I broke it down into negative 2u and negative 5u. Is everybody good with that? And then the last value stays the same. It's still plus 10. Okay? And then what I'm going to do is I'm going to pair these up. So this is my first pair, and this one is my second pair. And I'm going to do the same thing I did in an earlier problem, is I'm going to look at the pair of values, and I'm going to ask, what do they have in common? U squared minus 2u, what do they have in common? A u that I'm going to factor out. And if I factor out u squared divided by u, that gives me u. And negative 2u divided by 2u gives me negative 2. Now we're going to do the same thing with the orange one. 5u and 10, what do they have in common? They have a 5, and because this is a negative right here, we're going to write it as negative 5, okay? So if I do negative 5u divided by negative 5, what do I get? U. And what is 10 divided by negative 5? Negative 2. Do you see something that matches now? The u minus 2's match. If you did it right, that always will happen. It's not a happenstance, a coincidence or anything. It always will. So what does that mean? Well, it means that I've got this as one of my factors, u minus 2. And then the pieces that I didn't highlight, in particular, come on, there we go. The negative 5 and the u are the other factor, u minus 5. This is equal to 0. I've been sloppy. These are all equal to 0. Let me put those back in. So what can I do now? Because now the problem looks like number 1 and number 2 I started with today. Set them each equal to 0. U minus 2 equals 0. And u minus 5 equals 0. We'll add 2. We'll add 5. So this one becomes u equals 2. And this one becomes u equals 5. And that's the AC method. Okay, we're going to do the AC method again. I have w squared plus 10w plus 25. So the first thing I'm going to do is I'm going to write down AC. What is A in this problem? 1. And in all the problems you do today, it's going to be 1. In the next lesson, where they're not always going to be that way. What is C? 25. So this is 25. What is the B value? It's 10. So I want two numbers that multiply to 25 and add, you're already giving me an answer? Yeah, and add to 10. And Josh says that he thinks it's 5 and 5. Will that do it? 5 times 5 is 25. 5 plus 5 is 10. Okay, so what do I do with them? Well, I take the w squared and rewrite it. and I take the 10W and I break it apart. 10W breaks down into what? 5W plus 5W. That's the whole point of this answer right here, right? Was to use that to break apart my 10 plus my 25. And then I'm going to pair them up. All right, so W squared plus 5W, what do those two have in common? They have a W, right, good. So if I take a W out, what will I be left with? W, right? W squared divided by W is W. How about the other piece? Yeah, it's 5. So W plus 5. Plus, now I have 5W plus 25. I can take out a 5, you got it. And if I take out a 5, I'm going to have W plus 5. And did it work? Remember I told you, if I do it right, what's going to always happen? Those will have the same value inside them, right? And they do. So it worked. So I'm going to have W plus 5 from the orange highlighted pieces. And I'm going to have the W and the plus 5 from the green for another W plus 5. Okay, we're like 1 minute from finishing this up. What would I do last? Yeah, you'll set each one equal to 0. But what do you notice about this one that hasn't happened before? Yeah, they're the same. So we're going to get the same answer twice, which is fine. We'll subtract our 5. So we only have one answer on this one, W equals -5. Okay, so here's what we're going to do. Obviously, we didn't finish today. So I think you're probably not going to be mad at me if I do this. I guess we'll decide. What if we just don't have any homework over the weekend? Can you handle that? Yeah? Here's your homework assignment instead, since I'm out of time. Everybody gets to take a picture of your sheet from your Success Center, and you're going to email it to me. Okay? Can we make that the homework? Take a picture of your Success Center sheet and email it to me so I can get that recorded for your grade. All right. Sounds good.